Okay, time to use all these bright shining new toys and give us some answers. Now if you remember, what we're trying to do here is look at how the scale factor of the universe varies with time. So we've got time, and this is today, the present, and we can measure the scale factor by looking at the redshifts of distant things, and we can measure how far back in time by looking at the distance, as we've been talking about at great length, and so in principle we can work out the shape of this curve.
Yeah, so this is what I did for my PhD thesis, Paul, and so I was able to look back about 5%, so where the scale factor changed by about 5%, so a small amount, and I could measure essentially over what length that change of 5% referred to, and so that allowed us to measure the Hubble constant, how fast the universe is expanding now. And so for my PhD thesis, I got that the Hubble constant was 73 kilometers per second per megaparsec, plus or minus 9. And so that gave us an age of the universe, when you run the universe back in time, of about 14 billion years. And indeed, the person who brought me to Australia, Jeremy Mould, who was the director of Mount Stromlo at the time, was one of the 3 people leading the Hubble Key project, and they got 72 in kilometers per second per megaparsec. It's almost exactly the same answer I did. Their answer was better than mine, and that was in 2001. So we more or less agreed back then, using the techniques we've just showed you, that the Hubble constant was about this value of a little more than 70 was the best answer back 10 years ago.
And not that far different from the best answer now. So that was one thing, and that was telling us if you extrapolated back as a straight line, if the universe was really empty, it would be 14 billion years old. But of course the universe isn't empty, it's got matter in it, there may be not very much, we're not quite sure. So you'd expect it actually to be a bit younger than that, because the curve should curve down to some extent.
That's right. So if you had that critical density universe, that number is 2/3 of the age. So 2/3 of 14 billion years is like 10 billion years. And 10 billion years is a problem, because when we showed you the tip of the red giant branch diagram of that globular cluster, the nuclear physics tells us those stars are like 12 billion years old, and we want the universe to be older than the stuff in it.
Okay, so, but presumably you could take your method now. You were using type 1a supernovae to measure distances, and you can see them out much further than you've done in your thesis.
That's correct.
So in principle you could then actually look at one's way out, maybe halfway back to the Big Bang, and see, is their distance a bit shorter or a bit longer, and measure which of these curves you were at.
Yeah, that's right. So in our first course, we described the experiment in detail, where we looked back to when the universe was half its current age, to see which of these curves the trajectory of the universe was on, so we could get the real age of the universe from the Hubble constant.
Yeah. So this is the work that got the Nobel Prize. We're not going to go over it again here, because you can always go back to course 1 and have a look at it. But briefly, what did you discover? Which of these curves was it?
So, of course, when we looked down here, we found that none of these curves were the correct answer. Rather, we had a curve which seemed to be such that the universe was speeding up over time. And so, since it's speeding up in the past, it means it's probably going to speed up into the future. So that's it was a crazy result, and when we saw it, we of course thought we had made a horrible mistake. It took us a couple months to convince ourselves that our work seemed to be right. We weren't quite sure why, and quite frankly, we're still not quite sure why. But yeah, the universe was not doing what it was supposed to. It's not slowing down, it's speeding up.
And it turns out that how do we make this happen? Now, let's go back to the Friedmann equation we've seen many, many times. And it turns out that right back in the early days of this equation, Einstein had put a modification in here which could actually explain this. We've seen that normally the Friedmann equation will give you these things that curve downwards. But back then, Einstein had a problem. He looked at this equation and he'd seen that space had to either expand or contract. This was before Hubble had proven that the space was expanding. Einstein thought, it's ridiculous, space can't expand or contract. So he put a fudge factor in, lambda, over here, so that the universe could actually be stationary. It actually turns out it wouldn't do that because it would be unstable. But that was his idea, and then a year or two later Hubble came along and said, hey, surprise, universe is expanding.
12 years later, and Einstein said, oops, that was a big mistake. Why did I do that? I acted like a donkey, is what he was quoted as saying in doing that. And so when you look at this Friedmann equation, you can see you have this constant out here. And so when you're looking at the change of something over time is equal to a constant, Well, that's the equation for exponential growth. That's like the number of rabbits is equal proportional to the number of rabbits.
Yeah. So what
The
this
change in the
means
number of
is,
rabbits.
let's treat this side as a constant.
Yep.
Take the square root of a constant, it's still a constant. So you got a dot the rate of change of a equals a constant times a if you bring the that side of the equation. So the rate of change is proportional to the scale factor. So as the scale factor gets bigger, the rate of change gets bigger. So it gets bigger even faster. So it's even larger, so even faster. So the whole thing runs away. Now it turns out this is actually very similar to something we were talking about when we did inflation, because it's equivalent to having a constant density, a density that if you make the space bigger doesn't get diluted but remains the same. So it's actually equivalent to having a density of omega lambda equal to this value down here. And we saw what happened with that, because this is exactly what inflation theories tell you. If you get a constant density, you get growth that looks something like this.
Yeah, but the bizarre thing about our universe is that this exponential growth, we think, started about 7 billion years ago. And the universe is about 14 billion years old, 13.8. So it just happened about half the age of the universe ago. So we're right down here at the beginning of it.
Mm-hmm.
And that's a funny place to be. It's kind of unusual to have got something exponentially growing in the first E-folding, as we would say.
Yes, and we'll come back to that issue. So it's a real puzzle. Anyway, this is what was called dark energy. It just means it's something what makes this happen. So it might be the lambda that, but that's just a fudge factor. It doesn't have any physical meaning. It's just a number that Einstein put into the equation.
So dark is always a euphemism in astronomy for something we can't see or really understand very well.
Yes, so dark energy doesn't tell us other than it's something that does stuff and we don't know what it is.
Yep.
Good title though. Sounds exciting. So one possibility is exactly what we talked about for inflation, which is doing the same thing, driving exponential growth, that we have some field that fills the universe. I don't know what field it is. There's nothing really predicted by particle physics, but
There would be some undiscovered particle that's there and it has a field analogous to the Higgs boson, but not the Higgs boson.
Yes, it would have to be a much lower energy field and lower mass particle, otherwise it would all happen back at the era of inflation rather than now. So this is a very, very anemic, weak cousin of whatever the field was that drove inflation early on. And once again, let's arbitrarily assume it has the spontaneous symmetry breaking and this Mexican hat potential. And so it could be that about 7 billion years ago, the universe's energy came down to here.
Yep.
And it's now stuck in a state of false vacuum up there. And that this omega lambda is due to the gap between the energy of the universe and the energy up here. And presumably at some point, maybe 100 or 1,000 billion years in the future, maybe the universe will roll off the side and settle down. So inflation might be a transient era.
Yeah, it might be. And it may even be rolling off the side now. It turns out when it's stuck here, it looks just like the cosmological constant. And as it starts to roll down here, it changes a little bit. Its density, this is equivalent to the density changing over time. Mm-hmm. And so when it ends up down here, it could have a completely different set of parameters. But while it's up here, it's constant in its energy, and it looks just like the cosmological constant of Einstein's origin.
Yes, we'll talk a bit later about the attempts to actually measure whether this density of the dark energy is actually changing with time, because that might give us a clue about whether it's something like this. Another possibility is, in fact, the energy of the universe obeys a more standard single curve, but just that the 0 point is not at 0. So that even when you get a bit of empty vacuum, and at its lowest energy state, that energy is, there's still a 0 point energy. The energy is not 0 when everything's gone away and it's totally relaxed. So to make a bit of space as empty as you can, have nothing going on, it's still got an energy above 0.
Right, and to a particle physicist, this is a pretty ugly diagram because they don't think this should be a tiny little value. They think this might be a huge value, but a little tiny value, which appears to be what we see in the universe, that doesn't make a lot of sense to
them. They like this diagram, they don't like the fact that this is so small.
Yeah.
You would very easily have something like this where it's 100 orders of magnitude bigger, in which case inflation would have taken off very early on, or 100 orders of magnitude smaller, in which case we'd never know about this. But having this value that's...
Well, so they really want it to be 0. They'd like it to not even 100 orders of magnitude. They like it to be 0 or really big, which are the two natural values from their point of view for it.
So it seems like we need a particle physicist to talk about what could possibly be going on with this here. So let's go back to Lawrence Krauss and see what he has to say about this.